Hello, my name is Jürgen Dobay. In this video, I will talk about how digital twins can be used to enable the implementation of DevOps in cyber-physical systems. The results presented in the following are the results of a joint research effort of Graz University of Technology and Andritz Hydro. Andritz Hydro is one of the largest suppliers of hydropower plants, and thereby they contribute to the production of green energy for industry and households. Have you ever wondered what the ecosystem behind the energy production and delivery of energy from suppliers to our everyday life looks like? In the first place, energy must be produced. This is done by our energy suppliers. They either produce energy out of renewable resources such as wind, water, or the sunlight, or they use raw materials and resources such as gas, oil, or coal for energy production. In the next step, the produced energy must be distributed. Therefore, all the energy suppliers are connected to the power grid. To ensure grid stability, the energy production must be coordinated, which is supported through the usage of modern communication and computing infrastructures. As a private end user, we are typically not directly connected to this distribution network. Instead, we rely on customer services and smart product offerings to, on the one hand, consume energy from the grid and to feed in energy back into the grid. This coordinated ecosystem of industry sectors is an example of an ecosystem or principle that's called Industrial Product Service System, or IPSS in short. The principal idea of IPSS is that industry sectors build services around their products so that other industry sectors can use these services for a joint value creation. The overall goal is to maximize the value for all stakeholders involved in the process. Let's take a closer look on IPSS and the implementation. To implement the service offerings, IPSS, in the first place, use the capabilities offered of the underlying cyber-physical system. This cyber-physical system can be structured into a physical system and into a cyber system. The physical system consists of the physical assets that are embedded into a physical process. These assets and processes are controlled and coordinated by the cyber system. Together, the physical system and the cyber system create the value in the physical world. The core idea of an IPSS is to provide service-oriented access to these CPS capabilities for joint value creation with other IPSS. It is exactly the idea of this joint value creation that imposes new challenges and needs on CPS functionality and CPS design. In such an ecosystem of IPSS, the need for continuous optimization of the service offerings is evident. Today, this need is typically addressed through the optimization of processes and control parameters in the production process by the usage of digital twins and data-driven optimization techniques. While these techniques allow the online optimization of the value creation process, they provide no means to apply unforeseen changes on demand. However, such changes may arise due to unknown changes applied in other IPSS or unknown changes that must be applied within the own cyber-physical system. The source of such changes could be due to unknown requirements and service behavior at design time, due to changing customer needs, or due to technological evolutions, bugs, or security flaws in the software. To cope with these unknown changes, future cyber-physical systems must be capable to continuously adapt its cyber-physical system behavior by adapting its cyber system and physical system to changing needs and requirements. Which brings me directly to the research outline of our work. In CPS IPSS, there is the need to address the design uncertainty that arises from unknown changes within the cyber-physical IPSS ecosystem. To address this need, future cyber-physical systems shall be able to adapt the physical and cyber system to unknown changes. Our method to meet this goal is to transfer the DevOps principles from the ID domain to the CPS domain. Therefore, our strategy is the following. First, we design an architecture-based and self-adaptive and evolvable cyber-physical system. Second, we use the digital twin concept that is already present in CPS IPSS as a shared knowledge base. This shared knowledge base shall be used to manage the interaction between DevOps lifecycle phases and to enable the context-aware and self-aware autonomous adaptation of CPS physical and CPS cyber capabilities at runtime. Following this research outline, the remainder of this presentation is structured as follows. We just have motivated the need for DevOps in CPS. Next, we explain the digital twin concept, which we then use as an enabler technology in our self-adaptive CPS model and to coordinate the DevOps processes for CPS. In the fifth part of our presentation, I will show how the established self-adaptive CPS model can be used to implement A/B testing in cyber-physical systems. Finally, I will conclude the key messages of this presentation. The digital twin concept is closely related to the concept of digital models. A digital twin model consists of a physical thing that shall be modeled or replicated into the virtual space for design and simulation purposes. On the other hand, there is the digital twin. A digital twin also consists of a physical thing and its virtual replica. However, here the replication is done in an online fashion, which allows to implement a closed-loop control mechanism for live optimization and live prediction of conditions in the physical space. In between, there is the digital shadow principle, where an online communication link between the physical thing and its digital replica is established. This concept is primarily used for monitoring purposes. The level of integration increases from left to the right. So the level of integration describes the integration of the physical world into the cyber world. In the digital model, the physical world is disconnected from the virtual world and vice versa. On the other hand, the digital twin concept fully integrates both worlds into each other. Next, we take a closer look at the inner structure of digital twins. Similar to the previous figures, we have a virtual space and a physical space. To actually execute the virtual digital twin functions and services, IPC resources are necessary. These information processing and communication resources are illustrated by the yellow box. To implement the physical to virtual twinning, it is necessary to measure the states of our physical thing of interest. This physical thing might be implemented or integrated into a physical process. By measuring the state of our physical thing, we might also be able to measure the physical process state. These measurements are transmitted from the physical world into our virtual world, where some kind of realization mechanism is necessary to replicate the physical states into our virtual space. To implement the virtual to physical twinning, the process is inverted. Here we measure the virtual states and replicate those states for realization into the physical world. This closed loop control mechanism is called twinning. The accuracy of this twinning process is described by the digital twin fidelity. The digital twin fidelity is determined by the parameters that are replicated from the physical world into the virtual world and vice versa, and by the twinning rate of each parameter. The twinning fidelity also describes the capabilities of the twinning process. For a classical digital twin application, the twinning of process and control parameters is sufficient to achieve system optimization. However, if we want to implement DevOps, we must be able to twin changes that we apply to the system design in terms of software changes or data flow changes from the virtual world to the physical world. In essence, this means that the twinning process for DevOps must be able to replicate software changes from the virtual world into the physical world. Summing up the digital twin concept, a digital twin consists of three core elements: its physical instance, its virtual instance, and the communication link between these instances. The digital twin capabilities are described by the digital twin fidelity. The digital twin fidelity is determined by the twinned parameters and the twinning rate of each individual parameter. Next, we discuss our approach of integrating the digital twin concept into our self-adaptive CPS model. To that purpose, we first introduced the conceptual model of a self-adaptive system. According to this model, a self-adaptive system consists of three core elements: the managing system, the managed system, and the adaptation goals that control the behavior of the managing system. To that purpose, the managing system reads the adaptation goals, and based on that goals, the managing system adapts the managed system. The adaptation of the managed system might also affect the environment. To establish context awareness during adaptation, the managing system senses the environment. And to establish self-awareness during adaptation, the managing system senses the managed system. In the next step, we integrate the digital twin concept and the self-adaptive system model into the CPS context to develop our self-adaptive CPS model. Again, the CPS model is structured into its physical system and its virtual system. The physical system consists of the assets and processes used for value creation. Sensors are used to transfer the states of these assets and processes into the virtual space, and the distributed control services use this information for closed-loop control to influence the physical system behavior via the actuators. These elements of the CPS consist of mechatronic components and are at the heart of the CPS. Together with its IPC resource cluster, the mechatronic control infrastructure builds our physical CPS instance. Our goal is to replicate this physical CPS instance into virtual space and to create a virtual CPS instance in the cyber world. To that purpose, we set up services to replicate the mechatronic control infrastructure into the virtual space. Therefore, probes are integrated into the control services, and monitors report the states of these control services to the distributed digital twin services. These digital twin services perform the last step in the physical to virtual twinning process and realize the states in the virtual CPS instance. For virtual to physical twinning, the digital twin services read the states of the virtual CPS instance and forward the adaptation requests to agents that apply these requests to effectors which are integrated into the control services. By that, the behavior of the mechatronic control services is adapted, and at the same time, the mechatronic control infrastructure and physical systems are influenced. The adaptation goals are integrated into the system through adapting the virtual CPS instance, for example, during the execution of DevOps activities. In turn, the information contained in the virtual CPS instance can be integrated to coordinate DevOps activities. Again, the twinning fidelity determines the accuracy of the twinning process and the capabilities of the twinning process. From an implementation perspective, the twinning fidelity heavily depends on the capabilities of the effectors and probes and how they can be integrated into the control services. The more information can be extracted from the control services and the more properties of the control services can be changed, the easier the CPS can be adapted to unforeseen changes. From a model point of view, the managing system consists of the virtual CPS instance and its associated digital twin services. And the physical CPS instance comprises the managed system. Summing up, the digital twin is used as a shared knowledge base within our self-adaptive CPS model. This shared knowledge base can be used to establish context and self-awareness during CPS adaptation, and this context and self-awareness is established through observing the physical system states, the mechatronic control system states, and the IPC service and resource states. Next, we answer the question how this digital twin model can be used to manage DevOps activities and also to share knowledge between the DevOps phases. A typical DevOps lifecycle consists of 9 phases. In the first phase, business strategies are established and the design planning happens. Next, the design is implemented and continuously integrated and deployed using automated verification and validation tools combined with highly automated release and deployment processes. These release and deployment processes ensure that software changes are continuously deployed, integrated, and tested in real operation environments. Service monitoring is used to observe system operations and to respond changes in system behavior and performance from the operations space back into the dev space. From the digital twin concept, we already know that the digital twin is used during operations to optimize CPS functionality and for predictive maintenance. To this purpose, the digital twin uses monitoring data to simulate and predict the physical system behavior, and based on these predictions, the operations digital twin can optimize the CPS operations. We also know that the digital twin concept can be used for system modeling, simulation, and monitoring, which are all useful properties for CPS development. To increase the accuracy of the development models in the dev digital twin, or to enhance these models for the design and development activities, it is useful to transfer live data and historic data from the ops digital twin to the dev digital twin. The other way around, changes applied to the dev digital twin can be replicated from the development phase to the operations phase to either optimize CPS operations or to adapt the CPS to unforeseen changes. Looking at this depiction, we can use the digital twin capabilities for development and operation activities. And we can use the digital twin capabilities to exchange live data or historical data across the DevOps lifecycle phases. Next, we want to discuss our approach of integrating the DevOps lifecycle phases into our CPS using our self-adaptive CPS model. To integrate the DevOps lifecycle phases into CPS, it is necessary to consider the following 4 viewpoints. To enable the adaptation of the CPS in physical space and in virtual space, it is necessary to be aware of the CPS structure and organization as well as its functionality. This information must be reflected by the digital twin context to enable DevOps. Therefore, we take a closer look on these 4 aspects, starting with the CPS structure and organization from top to bottom. At the top level, the business and development activities dictate how asset and process control is implemented, which in turn dictates the behavior of the physical assets and processes during CPS operation. By comparing this hierarchical structure of the CPS to the DevOps processes on the right-hand side, we see that a plausible mapping can be established. Looking at the CPS functional aspects, a similar mapping is possible. The physical system implements the value-creating functions of the CPS. These functions are controlled by the software services, and the software services also manage the development and operation activities. Across these hierarchy levels, different requirements are imposed on the digital twin instances. On the lowest levels, where services implement the closed-loop control of physical assets, the twinning rates must be in the sub-millisecond range, whereas during CPS development, the twinning rate is less important. Summing up the previous figure, the digital twin can be used to share knowledge between the DevOps lifecycle phases. From an implementation perspective, the Dev digital twin shall be separated from the Ops digital twin to ensure that the digital twin instances can be independently developed and independently evolve over time. In addition, the separation of the digital twin reduces the digital twin complexity in terms of design and implementation, because it is able to design each digital twin instance for its individual usage needs within the lifecycle phases. Next, we will combine all the previously established concepts to implement A/B testing for cyber-physical systems. To implement A/B testing in CPS, we have to transfer the A/B testing strategies from the IT domain into the OT domain. To that purpose, we first discuss how A/B testing is typically implemented in an IT cloud environment. Similar to the CPS hierarchy, the business activities and processes are on top and dictate the development and operations activities. The DevOps processes have access to the IPC resources for development and also to the IPC resources that implement the user functionality. In this architecture, users can be placed at the same level as the DevOps processes because they use the same infrastructure services to access the provided functionality. If the current release is active, the load balancer routes 100% of the user traffic to the version 1 services. If we want to test a new release, first the necessary IPC resources are allocated and the services are deployed to the IPC resources. Next, the load balancer is configured to reroute a certain amount of traffic to the version 2 services. By monitoring and comparing the reaction of the users, it is possible to compare individual software releases, which is the core idea behind the A/B testing strategy. Next, we transfer the principles to a CPS architecture. As already discussed in the previous slides, the dev processes are separated from the ops processes. However, we can use the digital twin to interconnect these processes. Hence, the essential difference between these architectures are that the IPC resources in the OT network not be as flexibly managed as the IPC resources in the cloud environment, which is due to the hierarchical structure of the CPS. In addition to that, the hierarchical structure does not allow to use a central load balancer to reroute the user traffic to the different services. The users on the right-hand side actually represent the physical assets and processes that are controlled by our distributed services in the IPC resource cluster in the OT environment. With these initial considerations and comparisons between the IT and OT domain in mind, we next discuss the questions how we want to implement the A/B testing for cyber-physical systems. To that purpose, we revisit our CPS system-level views. Again, we start our discussion based on the CPS structure and organization on the left-hand side from the top to bottom. Looking at the details, the top level can be clearly separated into a business process and a development process. Next, we see that the control infrastructure can be separated into multiple layers. Similar to the control infrastructure, the physical system is separated into multiple layers. The asset controllers are responsible to control the behavior of individual assets. The plant controller is responsible to coordinate these assets and to achieve the plant goals. And the fleet management system is responsible to coordinate multiple plants. This hierarchical structure is also reflected by the functional view and the digital twin instances, where the services and instances are distributed across all layers. To establish a continuous communication link from the bottom layer to the top layer, the digital twin fidelity is adapted to the individual needs of each layer and the communication needs between each layer. With this hierarchical view in mind, we go one step further and investigate the design of an individual control device. On device level, it is essential to separate the critical processing elements from the non-critical processing elements. This separation must be established on the service layer, on data layer, and on the network and communication layer. To enable A/B testing for critical services, we have to deploy both services on the same control device because we cannot use a central load balancer to reroute traffic. To that purpose, these services must be also clearly separated, and each service requires its own digital twin instance. The deployment of services must be managed by the non-critical services. To establish the necessary context awareness for coordinated adaptation, the management services has an associated management digital twin instance. The interaction between the critical and non-critical services is well controlled by a mediator service. Looking at the critical components, they have to be designed for availability, integrity, and safety. In addition, these components must be designed for real-time processing and communication in the sub-millisecond range. Therefore, only the usage of OT tools and protocols is allowed. Looking at the non-critical components, they are also designed for availability and integrity. However, they can perform their processing and communication activities according to the best effort principle. This allows to use standard ID tools protocols, and network technologies. To implement A/B testing, we next integrate the device-level design into our system-level view. On the lower levels, we again see our physical assets and processes. Asset states are sent and transferred to the controllers. In the initial configuration of the system, only service A is active and processes the sensor signals and controls the actuators. If we start the A/B testing sequence, the management services are responsible to coordinate the entire sequence and to abort the A/B testing if violations are detected. As a first step, the service instances are distributed across the layers without starting them. Second, the communication links between the services are established to ensure coordination across levels. In the third step, the B services start to process the same sensor readings as service A. However, the B services do not send signals to the actuators and A can continue its normal operation. In this phase, the management service can observe the behavior of A and B for later comparison. If the performance of service B is satisfactory, B can take over control. The switching mechanism necessary for this can be easily implemented in software. To implement these mechanisms, it is necessary to strictly separate operations and management services and data flows, which can be achieved through the time-synchronous execution of services, priority-based scheduling, and priority-based data flows. Summing up the main design principles, it is necessary to clearly separate critical and non-critical tasks and to separate operation tasks from management tasks. As a consequence, we can achieve freedom from interference to ensure system availability, integrity, and safety by design. In addition, this clear separation enables the architecture-based adaptation and independent evolution of different system services and functions with different criticalities. As our main contribution, we can report from our evaluation that we achieved full CPS availability and integrity during CPS adaptation and during the high-fidelity twinning of CPS states during A/B test. With this, I conclude the key aspects of this presentation. With the presented research, we made the first steps towards the implementation of DevOps for CPS. To that purpose, we used the digital twin as an enabler technology to design a self-adaptive CPS model, to establish a high-fidelity context and self-awareness during adaptation, and to manage DevOps activities. As our main contribution, we can report that the development models can be used to provide full CPS availability and integrity during CPS adaptation and during A/B testing of critical CPS services.